Hi everyone, welcome back. We're going to be going through the second video of our local stability of first order systems, so we're going to go back through some of our theory, explain a bit, and also give some examples. So first, the main point of the last video was that we can use Taylor's theorem to approximate a nonlinear system of ODEs. Back in chapter 2, in video 2.8, we discussed basically the exact same thing for ordinary difference equations as opposed to differential equations, and basically all the same logic holds. So the first thing we did is, well, we had our regular setup, and then we showed that by using a change of variables and linearizing around our equilibrium, we get a new linear system. So what we did is we used Taylor's theorem. Of course, you start out with the value of the function at the equilibrium point, and then you use the Jacobian at the equilibrium, and then the Hessian at the equilibrium, and then the third derivative and the fourth derivative, etc. But since this is a linearization, we're going to ignore everything but the first two terms. And the first term is just equal to 0, and so that means that we get this here. That after our change of variables, we just have a linear system with the Jacobian matrix as the matrix defining the coefficients. Now, of course, since this is a linear system, that's homogeneous, autonomous linear system, we can solve it by just using the matrix exponential. Now, this is one of the places where some of you asked in class last week, like, why do we care about the matrix exponential when you can just solve it by using an ansatz instead? Well, it turns out that sometimes it's really helpful to be able to use the matrix exponential since you can prove more interesting things. So what we're going to do is we're going to write it using the Jordan canonical form. So just to remind everyone, this is a form where you have some matrix like this, and you have your eigenvalues. So maybe lambda 1, lambda 2, lambda 3, and so on. And then sometimes you have either ones or zeros above in the row above. So this is the Jordan canonical form of the matrix. And what you can do is you can decompose this into a matrix that's just all the diagonal terms and all of the terms in the row above, some of which are ones and some of which are zeros. So that's lambda plus n. And then by using matrix properties, you can rewrite it as the product of a bunch of matrices. So it's the exponential of t, j of tj is going to be equal to the p times the exponential of t lambda times the exponential of tn times p inverse. And so once you've done that, then all you have to do is you have to multiply these things out. So one of the things to notice is that n is nilpotent, which means that n to some power, in fact, it turns out that n to the, well, little n power is equal to 0. And this can be verified pretty easily by just looking at the fact that it's 0 on the diagonal and everywhere below the diagonal, and therefore this is a true statement. And plus, the power series, we can cut it off. So normally this power series would go to infinity, but we don't actually have to worry about that because all the terms above n minus 1 are equal to 0. And so we have a finite summation, and with a finite summation, things are a lot nicer. Here we also define the CM matrix, where it's just some n by n complex matrix that has no dependence on t. This is actually a real matrix, but that doesn't really matter. And we can compute it explicitly. We're not going to because it doesn't actually matter. All it matters is that this is some constant matrix with no dependence on t. And so what this means is that if you look at the matrix, this matrix, each of these terms is going to be some polynomial so this is going to be p1 of t, p11 of t, p12 of t, etc. Pnn of t. So where all your pij's of t are degree n minus 1 polynomials. And the reason this is important is because exponential of t lambda is a diagonal matrix with terms e to the lambda I t. But then what we can do is when you multiply diagonal matrix by a non-diagonal matrix, all you're doing is you're multiplying all of the entries of your non-diagonal matrix by the diagonal terms of your diagonal matrix. And so all the terms are going to be terms that are, well, they're actually going to be terms of the sort e to the minus, e to the, yeah. All the terms are going to be of the form e to the lambda I t times some polynomial pij, and probably pij of t, and so on. And we can look at that term by term, and since we only have t to the m power where m is less than n, well, you can just look at this, and that's pretty easily verify that that goes to 0 because exponentials go to 0 faster than polynomials can grow. And when you write that all out, you can pretty quickly conclude that that means that the limit as t goes to infinity of u of t is equal to 0, and therefore the limit as x of t goes to, sorry, the limit as u of t with t going to infinity is equal to 0, and the limit as t goes to infinity of x of t is equal to x bar. And so therefore it's the x bar equilibrium is locally asymptotically stable. Since if you start close enough that you can do this linearization, well, then you're going to end up going to x bar. On the other hand, if one of your eigenvalues has a positive real part, well, then the limit as t goes to infinity of u of t is going to be equal to infinity if u of 0 is equal to one of the associated eigenvector. Now, of course, the linearization may break down as the distance from your equilibrium grows. In fact, it almost certainly will, unless you have a linear system to begin with. But x of t will still go away first, and so it'll leave a sufficiently small ball around x bar, and so you can verify this with the actual definition of stability, but it's pretty easy to show that this is therefore unstable. So that's a rough sketch of the idea. Basically, you just had to make use of your knowledge of the matrix exponential and of your knowledge of the what happens when you use Taylor's theorem to linearize this higher order system. And again, as with difference equations, we define x bar to be hyperbolic if the eigenvalues are of non-zero real part and non-hyperbolic otherwise. Basically, if you have a hyperbolic system, you can say a lot more about it because you know that either all the eigenvalues have a negative real part, in which case you're stable, or at least one of your eigenvalues has a positive real part, in which case it is unstable. And we can specialize this down to the two-dimensional case. And all that is basically, in the two-dimensional case, we can entirely characterize the eigenvalues by the trace and determinant, as we did in the previous, in some previous videos. And therefore, well, you can talk about the stability and instability and local asymptotic stability of a two-dimensional system. Let's give an example now, since we've covered a lot of theory. So this is example 5.11 in the book. It's going to be a predator-prey model. So we talked about this a little bit in the difference equation section for discrete systems. But now we're going to talk about a continuous predator-prey model where x of t is going to be equal to the density of the prey species. Y of t is going to be the density of the predator species. And we're going to assume that this has the following form. So dx dt is going to be x times r minus r times x over k minus ay, where r, k, and a are greater than 0. And dy dt is going to be equal to y times minus b plus cx, where b and c, these constants, are greater than 0. So now, one of the things that you should note is that this part here, if you ignore the minus ay part, this is just logistic growth. So we're using the logistic growth model. So if there were no predators, so this here is the predation term. If there were no predators, the prey species would just grow logistically until it reaches its carrying capacity. So this is its carrying capacity. And this here is the growth rate. Okay, and for our predator species, we also have some natural death rate, and we have predation. So it's growth as a result of eating the prey. Growth as a result of eating prey. Okay, so now that we have this model, we can analyze this. One of the first things to notice is that if you start at 0, x of 0 is equal to 0, well then x stays at 0 for all time. X of t is equal to 0 for all t greater than or equal to 0. And if y of 0 is equal to 0, so if you have no predator to start with, then you'll also never have you'll never have any predators. So this makes sense intuitively, because if you have no prey, then you can't have any prey in the next generation. The number of prey can't increase, and the same for the number of predators. It is important to verify that your model mathematically models the assumptions you have about the real-life system. So now, if you had spontaneous generation of predators, well, then it's not really a predator-prey model anymore. And so this is a useful sanity check that our model actually does seem to correspond with at least some of the properties of the real-life biological system we care about. But now, this has a couple mathematical consequences. So the first is because this means that trajectories, so remember that trajectories, if your system has continuous partial derivatives, which the system does actually have continuous partial derivatives everywhere, so trajectories cannot cross. So the trajectories cannot cross, and therefore positive solutions cannot cross Euler axis. Cannot cross Euler axis, plus the positive quadrant, x of 0 is greater than or equal to 0, y of 0, the positive quadrant where x is greater than or equal to 0 and y is greater than or equal to 0 is something called positively invariant. More precisely, that means that if x of 0 and y of 0 are in the positive quadrant, then x of t, y of t are also in the positive quadrant for all t greater than or equal to 0. So pictorially, what this looks like is if something starts up here, well, it can go around, but it can't ever cross the axes. So this makes sense because, well, you don't want your model to be able to have negative numbers of predators or prey. So that is just aphysical. Okay, so basically these are just some quick sanity checks that are the model we wrote down here. So I wrote down some mathematical model, and one of the sanity checks you have to do as a mathematical biologist is check whether or not the math I wrote down corresponds with what we believe to be the state of the world, that we believe to be the state of reality. And we believe that the state of reality is you can't have a negative number of animals, at least in this kind of ecological model, and therefore our model should also not admit negative numbers. And it turns out that this is the case, and so we're happy. So now, how do we solve this? Well, in order to solve this, we want to first find the equilibria, and it turns out that there are going to be 3 equilibria. This is basically where dx and dx dt and dy dt are both equal to 0. So we have 3 equilibria. So we have 0, 0, k0. So note that these are the same equilibria that you just get from the logistic equation for prey growth if you don't have any predators. And let's define another one, which is x bar y bar is equal to, this is the more interesting non-trivial equilibrium, b over c times r times the quantity of ck minus b over ack. Okay, so we'll get on that in a moment, but first, let's hear this equilibrium is no predators or prey. So if you have no animals in your system, you'll never have any animals in your system, and that's an equilibrium. This here is the only prey, no predators. So this is the standard logistic growth equilibrium. Well, this is the, if you're at your carrying capacity, you're not going to go up or below if you're just doing standard logistic growth. And the third equilibrium is the more interesting one, where you have some balance between predators and prey. And one of the things that we'll notice is that this is positive only if k is greater than b over c. And note that b over c were respectively our death rates and our growth rates in our this equation over here. And if your death rate is, if your carrying capacity isn't greater than b over c, well, then the prey population isn't large enough to support your predators. So if negative, prey population not large enough to support predators. Okay, so biologically that says, well, if you only have a very few prey animals going around, so if you're on the African savanna and you only have 5 wildebeest, that's probably not enough to support a bunch of lions. And so in that case, the predator population will completely die out, and you're going to be left with this equilibrium layer instead. Okay, so now let's try to analyze the stability of each of these equilibria. So that's what this entire lecture has been about. So let's go ahead and let's copy down our equation again, just so that, let's see, dx dt is going to be equal to x times r minus r times x over k minus ay. And dy dt is equal to y times minus b plus cx. Well, we can compute the Jacobian matrix. The Jacobian of xy, that's going to be equal to r minus 2rx over k minus ay minus ax cy and minus b plus cx. That's just taking the partial derivatives of each of our functions with respect to x and y. And so therefore we have j of 0, 0 is going to be equal to r 0, 0 minus b. And let's see. And we also have j of k0 is going to be equal to minus r minus ak, 0, and minus b plus ck. And let's deal with the third equilibrium in a moment, since that's the more complicated one. So for each of these two equilibria, well, this is a diagonal matrix. And so if you have a diagonal, this is a diagonal matrix, and since you have a diagonal matrix, that means that the eigenvalues are just along the diagonal. So lambda 1 is equal to r, and lambda 2 is equal to minus b. Recall that both of our, that all of our constants that we chose to be positive, and so this implies that this is a saddle point. And so you have one positive and one negative equilibrium. So this is a saddle point, and it's unstable. Here, well, this one here is a triangular matrix, and therefore you can again read the eigenvalues off the diagonal. So let's say lambda 1 is equal to minus r, and lambda 2 is equal to minus b plus ck. And note that this has the minus r is always negative, so we only need to look at whenever lambda 2 is positive or negative. So if k is greater than b over c, when lambda 2 is greater than 0, so this is a saddle point, and it's unstable. And if k is less than b over c, when lambda 2 is less than 0, so this is a stable node. It's a node because this is a because it's non-imaginary. So, okay, so now let's take a look at the third case. So in the third case, we had x bar is equal to b over c, and y bar is equal to r times ck minus b over a ck. So when you plug in those values into the Jacobian, what you get is you get minus rb over kc minus ab over c, and r times ck minus b over ak, and 0. And now, in order to analyze this, it's a little bit harder. You can directly compute the eigenvalues, but another alternative is just to use the stability diagram based on trace and determinant. So remember, this was tau is equal to trace of j, and this was determinant equal to determinant, I think we call it delta. So delta is equal to determinant of j. And what we had is we had a parabola here that of the discriminant determining whether something was a spiral or not. Tau squared is equal to 4 delta. So here we had a stable spiral on this side, an unstable spiral on this side, an unstable node here, and a stable node here, and a saddle point down in the lower half plane. So this was our stability diagram, and now all I have to do is we have to take a look at the trace and determinant of j. So trace of j, that's easy. Let's just sum together the diagonal terms. That's minus rb over kc. Minus rb over kc. Well, we chose our constant to be positive, and so this here is strictly negative. And so therefore, we are, that was the trace, and so therefore, where was I? This is the trace axis, and this is the determinant axis. Trace is negative, and so therefore we're in this section. So entirely in this half. Okay, well, let's take a look at the determinant. So determinant of j is going to be equal to, well, these terms cancel out to 0, and so you only have the other two terms to worry about. So determinant of j is equal to ab over c times r times ck minus b over ak, which is greater than 0 if k is greater than b over c. And this is, of course, because we only care about this equilibrium when it's positive, and so we're going to analyze it when k is greater than b over c. So if that's greater than 0, then that means that we are in this region, right? So together, these imply that x bar, y bar is locally asymptotically stable, since both of those are stable. Asymptotically stable if k is greater than b over c, which is necessary for it to be positive. And now, of course, we also have the discriminant. So discriminant is gamma equal to trace of j squared minus 4 determinant of j, basically corresponding to whether you're above or below that parabola, which is equal to minus rb over ck squared minus 4 times rb times ck minus b over ck. And I'm not going to actually solve this, but basically if the discriminant gamma is greater than 0, then it's a node. If discriminant gamma is less than 0, then it's a spiral, because that determines entirely whether it's on this side or on this side. Let me put that in. So then it's a spiral or it's a node. Okay, so that was applying all these ideas about linearizations of nonlinear systems, and you can apply the same stability analysis around each of the equilibria. So this should be old news to you all now, especially since we did something incredibly similar for the difference equations. The major difference here is that instead of caring about whether the eigenvalues have magnitude less than 1, we care about whether the eigenvalues' real parts are less than or greater than 0. Okay, Thank you very much, and I will see you in the next video.